Hey, what's up, guys? Today, let's look at the Lintcode problem number 12, min stack. What do we need to do is that we need to implement a stack with the main function, which will return the smallest number in the stack. It should support push, pop, and main operations, all in a one cost. Let's look at this example. For example, we have a main stack, and when we do a push, and right now we have 1 in our stack. When we do a pop, and then pop just pop out 1. When we do a push 2, push 3. So right now in the stack we have 2 and 3. And when we perform a main operations, then it's gonna return 2 because we have 2 and 3 in the stack. If we push 1 into the stack, when we call the main, it's gonna return 1. So basically, we just need to implement this main function in the stack. Let's look at the right side. But before we do that, we need to analyze what is the strategy, how we approach this problem. So for stack, we know that a stack can do a push, can do a pop. But now we need to implement one more option, min. And we need to implement it in O1 cost. So somebody probably without these constraints, somebody probably will think that when we call this main, we can just loop through all the elements in the stacks and we just calculate the smallest one and just return. So this time complexity is really high. If we have main, if we have n elements in the stack, it's gonna be like a on if we have to look through them. Question is about that. Do we have a higher, better, more efficient ways to do it? So in this problem, it's going to be a min stack. So let's look at the right solution area. So for the initialization, we have a stack. Before we do that, we just go over the stack first. We have a stack. We use a stack is a list in Python. So we use this list to save the data. And when we do a push, we just always push the data into the stack. So when we do a pop, we just always self.stack.pop. By the way, in Python, Python's array or list, it just itself is the stack. So we don't have to use extra API. So when we have a min options, then what do we have to do? The solution is we use another stack. We call it a min stack, and then of course it is the Python list. So when we call main, we're going to just return the top of the min stack. So because we just maintain the top of the min stack, so its cost is always 1. So problem is that in order to make this happen, we need to do some magic when we push data into the stack and pop up the data out of the stack. So how should do it? So when we push the data into the stack, we need to maintain our min stack. There are two situations. If our current min stack is empty, that means we never push anything into our min stack. We're gonna just push this number into this min stack. Remember, the min stack is to help us to maintain the current min or smallest value in the stack. Maintain the smallest value in the stack. Always put the smallest value, smallest elements on the top of the min stack. So if there is no data in the min stack, we just push this number into the min stack. That means the current number is the smallest element. But if we already have some value in the min stack, if we push another number into this stack, so we're gonna check that if this number is less than current smallest elements, or that is the top of the elements in the min stack. If it is, that means currently the number we push into the stack is gonna change our the smallest elements of the stack. So we're gonna just have to push this guy into the min stack. Only when this thing happened. If bigger number pushed into the stack, we don't care. We don't have to do this. So when we pop out elements, what do we have to do? So here we have to check that the popped out, the element is about to pop out, is the top of the stack. If the top of the stack's element is the same as the elements on top of the main stack, that means we're gonna pop out the smallest elements in the stack. Then we also have to do a synchronization. We have to pop it out from the main stack. So this is this part, this one, and this one is how we maintain the main stack. The remaining operations just a regular stack. So this is the whole idea. Let's just run this algorithm. That works. That works. Last, I still want to emphasize this part. When we push the data into the main stack, we push the data into the main stack only when the data is going to change the smallest elements of the stack. When we pop out the data into this out of the main stack only when the data we pop that out is the smallest data of the current stack. So remember these two things. So that's why our data stack can be really huge, but our main stack can just be concise because we only save the data that is going to change our smallest value. All right, that's today's algorithm. Thanks.